Hello. Today's video, I want to talk a little bit about one-sided limits in calculus. Now, I realize this is not, necessarily a deep or esoteric topic, but there's some lovely examples that will help display some of the aspects of one-sided limits. So let's go to share screen and see what we got. Okay. And you can see that my equipment's a little antiquated. So let's talk about one-sided limits. Now, I'm assuming you know what the definition is, but we'll say, just to remind you, we say that the limit as x approaches a from the right of f of x equals L if for every y tolerance epsilon greater than 0, there is a related um, x tolerance delta greater than 0 such that x minus a being greater than 0 less than this delta means or implies the difference between f of x and L is less than epsilon. And similarly for left-hand limits. Basically, what that means is what happens here, it's a minus x instead. And the typical thing that you would see in many calculus books, and it's a thing that you should see, is you'll have something that has a jump discontinuity. Like for example, you might have a function. Let's say this is comes to here. Let's say this is 1, 2, and this might be 1, 1. And you'd have a line like that. So your f of x might be something like, in this case, it's going to be x plus 1 or x less than 1, and it's going to be x for x greater than or equal to 1. And what we can see is that the left-hand limit, as x approaches 1 from the left, would be 2, and the limit as x approaches 1 from the right would be 1. And of course, these don't match, so the limit doesn't exist. That implies limit as x approaches 1, f of x does not exist. And we can poop up this example with other things. Now, what I'm getting at is that in this particular thing, you have a piecewise defined function, and you pick a formula to apply to one, and I realize these things do occur. There are in applied math some functions that have these jump discontinuities. Jumping means you have this big uh, gap like this, but I think you can find a really lovely example. And I mean, this is well known, but I just like it anyway. So let's look at a different example here. And the example I'm going to start with is y equals e in, let's say here, minus 1 divided by x. Now take a look at that. And as you can see right here, and let's just go ahead and analyze this. In fact, let's just take a picture of this. I have different keyboards. But let's just take a picture of this and just so I can draw on it. And this is a lovely little function. So copy there, and then let's just paste it in our other one. And let's just see where to go to town on this one here. Now again, this function is f of x equals, oh my gosh, I already forgot what I said it was. Oh, that was minus 1 over x. Okay, we can deal with minus. That's good. You don't really need the minus, but e to 1 over x would work just great too. And we can see right here, as x approaches 0 from the left, minus 1 over x approaches, well, minus infinity. I know this is highly informal, which means to say this approaches infinity. So then e to the infinity goes to infinity very quickly. So you can see that right here. But as x goes to 0 from the right, minus 1 over x goes to minus infinity. And we see, well, that e to the minus infinity goes to 0, as we can see here. So the left-handed limit x approaches 0 from the left equals infinity, and the limit as x approaches 0 from the right equals 0. So needless to say, the limit does not exist. And it becomes unbounded. But what's nice about this, and I should be good, I should say x not 0. You can make it 0 at x equals 0, I guess. But point is that you have a single formula, and again, you don't really need the minus. But we can see that this shoots up, so you have an one-sided asymptote, then you have something approaches 0. So when it comes to one-sided limits, you can have weird stuff like this happening. But there's more, and this is the real example I wanted to get at. And now let's just alter this just a little bit. So let's talk about the sign of this. And this is going to be a really lovely thing here. Now look at the left-handed limit at this case, this thing here. Notice how this oscillates on the left side, then goes to 0 at the right side. So let's uh, make another picture here. Let's do this one. And this particular example, lovely example, we'll study this just a little bit. We can see what's going on there. From the left, sine of e to the minus 1 over x oscillates infinitely often, and by between -1 and 1. And we can actually easily see this. So for example, if we set e to the minus 1 over x equal, let's say, an integral multiple of pi, where k is an integer, taking the log of both sides, and then solving for x is not going to be that bad. We get that x is equal to minus log over k pi. And we can see that this occurs or we can write this as log of 1 over k pi. This oscillates infinitely often, right? Because this number here, as k goes to infinity, 1 over k pi goes to 0. And let's see, I want to make sure I did this right. Took the log of both sides. Oh, I just screwed this up big time. Oh, well, that's all right. That's what I wanted. Darn it. So now you lost complete confidence in me, but that's okay. This is a fun little video, so I'll just handle the screw up here. So I'll just do minus x is 1 over log of k pi. X is minus 1 over log of k pi. And these things do indeed march to 0. It would be easier without this negative here, all right? But as you can see, as k gets larger, 1 over k pi gets smaller. And we also know that log of 0, log of 0 is undefined, but it tends to negative infinity. So, but that's in the denominator, so we have numbers getting arbitrarily close on the side to 0. So that's these gray points right here. These are these gray points right here. So you have an infinite number of points where this is going to be 0. On the other hand, if we want to look at these points where the function is 1, we have, let's say 1 over x is equal to pi over 2 plus 2 k pi. Same sort of thing on log of pi over 2 plus 2 k pi, or x is minus 1 over log of pi over 2 plus 2 k pi. And as k goes to infinity, these numbers get arbitrarily close to 0 from the left. So we see this, this is sine 1 over x kind of behavior on the left-hand side. So we see these things bunching up as expected, right? But there's more. But on the right-hand side, this is where it gets fun. On the right-hand side, let's see right here. On the right side, again, as x approaches 0 from the right, that means x is positive, minus 1 over x approaches negative infinity, and e to the minus infinity goes to 0, and we see that right here. So then we get sine of 0 when you plug that in. So we do have a limit from one side. The limit as x approaches 0 from the right, sine of e to the minus 1 over x is 0, and the limit as x approaches 0 from the left of sine e to the minus 1 over x does not exist, but it doesn't exist because of an asymptote. It doesn't exist because of this infinite oscillation. Now, let's do one more and we'll close this up. You probably know where this is going. Let's say we want to make this continuous at the origin. Well, we know what to do. Just add up the good old factor of x. We see that. Just use the factor of x here. And that is kind of a neat thing because this side here is not affected. The right side is not affected. So we'll just write this thing down. This is f of x equals x sine of e to the minus 1 over x. Now, on the right side, still goes to 0 for the same reasons. But the left side, what you see here is you see that sine of e to the minus 1 over x is always between 1 and negative 1. Then if you multiply through by x, but keeping in mind x is negative, so we have to change this. This is minus x and x. Now this looks strange. Remember, x is less than 0, so this is really positive and that's really negative. And what we're doing, and I'll do this in black, this thing right here that I'm drawing in black, you can think of this is a graph of y equals minus x. So you see that's actually the upper bound. Then if I do this and draw this line here, this line in blue, that's really y equals x, and that's actually the lower bound. And then we can finish this up as that, you notice that the limit as x approaches 0 from the left of x is 0. The limit as x approaches 0 from the right, I'm sorry, 0 from the left of minus x is also 0. So by the squeeze theorem, the limit as x approaches 0 from the left of sine of e to the minus 1 over x is also 0. Oh yeah, and I did make that blunder. I forgot to put the x there. Yeah, that I had to do. You know, when I did this, I did all the switching and I forgot to write the x here. So sorry for all the sloppiness here. But I do think that's a nice, lovely example. And you get the squeeze theorem behavior from one side. The other side is just a composition of functions type theorem. So, okay. So that's it for today, and thanks for watching.